We're going to be looking at perception, how we look at things, and patterns, which are the things that happen within perception, where we make patterns. And I'm going to start by telling you a very important story, and if you remember this story for the rest of your lives, it'll do you a lot of good. And it's a true story, which happened to me years ago when I was at Oxford, and in those days you had to be back in your college by midnight, otherwise they closed the gates and you had to find your own way in. Well, my first night there, I was going off to a party in London, so I asked one of the old hands who'd been there before how to get back in. And he said, it's very simple. You go along and you come to a wall, you climb it, you come to a second wall, you climb that, and you find yourself inside. Well, I came back at about 2:30 in the morning, and you have to approach from this direction because there's a police station somewhere down here. And I came up to the wall and I climbed it, and I went along and I came to the second wall, and I climbed the second wall, and I found myself out in the street again. I then went all the way back, climbed the wall, went along, found another wall, and this time I thought I'd explore, which I did. Found a gate which offered much easier footholds to climb, got to the top of the gate, and I was sitting astride the top of the gate when the gate swung open. It had never been closed. Eventually I got in, and that's since become a classic tale of idiocy, which has been told back to me on 2 occasions, people forgetting that I was somewhat involved. Now, the purpose of the story really is to illustrate a very important point in thinking, which is this, which is that excellence in wall climbing does not itself mean that you're climbing the right wall. And in thinking, if we divide thinking into 2 stages, we can look at what we might call the perception part of thinking, how we look at things, and then the processing part of thinking, which is what we do about them once we've looked at them. So climbing the wall is processing, perception is deciding that's the right wall to climb. Now, quite often in thinking we put all the emphasis on the processing, but I think that in general, most of the important part of thinking takes place in the perception area. And that's what we're going to be looking at today. What happens in perception, how we look at the world, how we generate our ideas about it. Let me ask you a question. That's a noughts and crosses game area, and we'll just put a square around it for the moment. So it's 9 squares. Suppose I start in any square, and I move to any square next. Just give me an idea how many possible routes, how many possible ways might there be of going through that noughts and crosses grid. I'm going to ask you for suggestions. How about you? Just guess. 4. Gentleman behind.
Several hundred.
Several hundred. All right, anyone?
27.
27. Well, as far as I know, and I could well be wrong, the number is something like 362,880. Because you multiply 9 by 8, by 7, by 6, by 5, by 4. Now, some time ago, some years ago, I invented a little jigsaw puzzle, which had only 16 little square pieces. And what you had to do was to arrange these to make a big square, which was 4 by 4. But there was a catch in it. It was so designed that you couldn't tell you'd got the right answer until you'd placed every piece in the right position. So you had to try out trial and error. Now, with trial and error, even if you put one piece every second, day and night, without stopping to eat, drink, or sleep, in order to be sure of solving it, it would take you, as far as I calculated, but that's open to question, it would take you more than 1,000 million years to solve this simple jigsaw. And since man's only been on Earth in any form for 10 million, and even the termites for only 100 million, it's something you give to your enemies for Christmas. Now, the reason I mention these is that the mathematics of combination are huge. And if we had to try and cross the road, by standing at the side of the road and really analyzing all the information that came towards us, it would take us about a month just to cross the road, as we analyzed all the data. But we don't take a month to cross the road. We cross the road in very normal time, a minute or 30 seconds, 20 seconds. The reason we do that is that the brain is designed to be brilliantly uncreative. That is the main purpose of the brain, to be brilliantly uncreative. The main purpose of the brain is to take in all the information and as quickly as possible put it together to give a pattern. And once we have the pattern in future, let's put the pattern down here. It's like a track or road. In future, once we have the pattern, all we need to do is just recognize the beginning of the pattern, not analyze anything else, just read out the rest of the data. It's a wonderful system for making sense of the world and allowing us to operate on it. Whereas if we were working in these sort of figures, we'd never be able to cross the road. So the brain operates to make patterns and then use them on every possible occasion. And if something is even remotely similar to the pattern, then we will treat it as if it was that particular pattern. So it's a wonderful device for allowing information to organize itself into patterns. We recognize the pattern, and then we go on to the next pattern, and we go on to the next. It's rather like with the Rubik Cube, which some people are very good at doing. And one of the ways to do it is you recognize the pattern you get, and then you know what to do next. That produces another pattern. You recognize that, and you go on, and you go on. Anyone here who's a whiz at doing the Rubik Cube? All right, Dinah, would you give the gentleman the Rubik Cube? There we are. Now you start off with it. Okay, we'll come back to it a bit later. Now, in making these patterns, the brain is very different from a computer. Totally different from the way a computer works. Let's contrast the way the brain works with a computer in a sense. Imagine we've got a tray, and the tray is full of sand. And what we do is we drop a ball, a steel ball, on the sand. And it gets embedded in the sand where we've dropped it. In other words, it stays exactly where we've dropped it. The sand will give us an accurate record of what we've done. This is a passive surface because the ball will stay exactly where we've dropped it. We drop it here, the ball will stay here. Most of our information systems are of that type. But let's contrast that with another type of system. And in this other type of system, the surface is shaped like this. Imagine a plastic surface shaped like that. Now, no matter where we drop the ball on this surface, it will always end up in this same position. If we drop it here, it will roll along. If we drop it here, it will roll along. So no matter where we drop it, it's moved to this position. This is now an active surface because it actually changes the information. In a sense, it curves the information. Now let's move to the next one, the next type of system. And the next type of system, we have a tray. And this time we've got heavy oil or treacle or molasses in there and a rubber membrane on top. And we drop the first ball on it, and the first ball sinks in gradually into the molasses or treacle. It then shapes the surface like that, so when we drop any other ball there, it rolls down and ends up near the first one. So this is similar to this surface in that the information is altered as it's received, but there's a difference that here the shape is determined by some outsider. Here the shape is determined by the information that comes in. So let's move on to another pair of models which show this even more clearly. Imagine we have an ordinary towel put on the surface, and alongside that we have a bowl of ink. And we put a spoonful of ink on the surface. There's our spoon. Spoonful of ink on the surface leaves a stain. Another spoonful, another, another. At the end, we have a good record of all we've done to the surface. If we wanted to use that, we would have to come along with what we call a processor, an outside processor, which would measure or relate the information. Now, that's the traditional way we think of the mind. Memory, thinking, traditional view of a computer, storage, processing. But let's contrast that with another system. In this other system, our surface is not a towel. The surface is a shallow dish of gelatin, or what we call jelly, what the Americans call jello. Looked at from the side, there it is. This time we'll heat up our bowl of ink on a little fire. When we put a spoonful of hot ink on the surface, while it's hot, it dissolves the gelatin, and when we pour away the dissolved gelatin and cooled ink, we're left with a little dip, a little depression in the surface. That corresponds to the ink stain. We repeat, 2, 3, 4. But this time we get something very different. We get a channel like that sculpted in the surface or carved in the surface of the gelatine. What has happened is that if our second input is near the first, the wetness spreads, it flows into there, makes that deeper, that stays quite shallow. And similarly with the next one. So in the end, we get this channel. In other words, the input has been linked up. So what essentially we've got is that the gelatine has provided an opportunity for the incoming information to organize itself, that's the key word, to organize itself to give a pattern. And what do we mean by a pattern? It means that when we start somewhere, we're taken along to somewhere else. So if we started here, we would move along and end up there. Quite different from this system, where if we started there, we just stay there. Now, there's various other ways of showing it and how the nerves work in the brain, but essentially what we're looking at is a system, an active information system. Quite different from computers and all other systems we use, and what it does, it allows incoming information to organize itself into a pattern, which is what we talked about when we said crossing the road, the mind has put together all the information to give a pattern so you recognize motor cars and so on. So what we're going to do now is have a look at patterns and how we use patterns. Before that, let's do two things. Let me ask Dinah to collect the Rubik's Cube, which I think has been done. Well done. Dinah, can we collect that? Well done. Well done. So that's very experienced use of patterns. Now, let me ask a question. What do you think the purpose of thinking is, in general? Anyone? Any suggestions? What do you think the purpose of thinking is?
Essentially to make sense of the world that we live in.
To make sense of the world we live in. Okay, some other suggestions?
For survival.
For survival. All right, I'll tell you what the purpose of thinking is. The purpose of thinking is to abolish thinking. In other words, the reason we think is really to find the nearest pattern and lock into it, and then we don't need to think anymore, we just follow the pattern. Let's move on to another exercise in pattern recognition. And what I've got here are some shapes which I'm going to put up out of focus. I'm going to put these up out of focus. And I want you, when you think you can recognize the shape, I want you to say immediately what you think it is. When you think you can recognize it. I'm going to come down slowly. When you think you can recognize it, say immediately what you think it is. Any offers? Any offers?
Tree. Tree. Two rabbits.
Tree with two rabbits. Absolutely correct. Good. So as soon as you recognize the pattern, you snap into it, and you're away. Let's have another one. As soon as you recognize it, call out as you did before. I'm going to come down slowly. Any offers? Anyone?
What's the man?
What's he doing?
Looking over the fence.
Leaning on the time.
What's he doing?
Drinking a pint of beer.
Drinking a pint of beer. So we're looking at patterns and how quickly we can recognize patterns. So recognition is one of the use of patterns, but of course sometimes it can go wrong. So we're going to look at a situation where it's difficult to tell which pattern we should be using. Dinah, let's have a look at the spool. And what we've got here is a spool with a cord wrapped around it, and Dinah's going to lay it out for us. Okay, and now she's going to roll it partly back till it's halfway along. And then I'm going to ask you, let's leave it there. Three things can happen when she pulls on the cord. It either comes towards me, away from Dinah, or it stays exactly where it is and spins, or it rolls itself up and goes towards Dinah. How many people, hands up, think when she pulls on the string, it will unroll and come towards me? All right? How many think it will spin and stay where it is? How many people will think that it will actually roll itself up? Okay, Dinah, you go ahead and pull. It rolls itself up. So there, when we're using the unrolling pattern, we're actually using the wrong pattern for that situation. Let's look at another one of these. Someone wants to give as a present a rather nicely carved block of wood, which is made of two different sorts of wood. And the two different sorts of wood are dovetailed together with a dovetail joint. The bottom wood is a dark one, the top wood is a rather lighter one. Now, the question I'm going to ask you is, would it be possible to make that sort of block with the two dovetailed together? Looks just the same from each side. And if he did make it, would it be possible to separate those two blocks? Let's have some suggestions. Those who think it would be possible to make it, first, would it be possible to make the proper dovetail joint thing? Those who think it would not be possible. All right? Those who aren't thinking. All right. So it seems impossible. So let's ask Diana to show us the impossible block. There we have the block. Now let's see if it can be, it looks the same from each side, proper dovetail joints. Let's see what happens if you try and undo it, Diana. Well, we see that it slides off very easily. Now what has happened, there we are, that's how it works. What has happened is this, that the pattern we normally use is we expect the joints to go like that because that's the normal pattern. But in fact, as we see there, the dovetail joint lines go like that, and we just slide one off the other very easily. So one of the difficulties with using patterns is if we get to use the wrong pattern, then we're in trouble. So let's move on from that, and we're going to look at something else to do with patterns. We looked at recognition, now we're going to look at abstraction. I'm going to put some shapes up here, and I'm going to ask you to tell me what they have in common. Something, some pattern we can abstract from them that they have in common. Let's have some suggestions. Just put up your hand and I'll know where to go. Let's have the lady in the middle of the, over there.
They're all made a straight line.
They're all made a straight line. Something else they have in common. Gentleman in the middle over here.
They could all be made out of squares.
They could all make out of squares, in fact 5 squares in each case. All right, anything else? Anything else?
They've all got right angles in them.
They've all got right angles. All right, since they've got right angles, they could all be made out of 5 squares. They could also be letters of the alphabet. That's a rather large I admit. So when we're looking at patterns, we often have to say, in this situation, what pattern can I take out, what pattern can I abstract from the situation? So when we're using patterns, we use them for recognition, we pick them out of situations, we abstract them. Now we'll go through another exercise in that. You've got a little card in front of you. Just put down any noun, any object, any familiar object you like, just write it on that card. All right, those will do. All right, I'm just going to write down the ones you've written quite straightforwardly. I'm not going to try and choose them in any way. I'm just going to write them over here. Rather interesting ones, I must admit. Jumper. Apple. Car. Desk. Another car, we'll drop that. Glove. How many is that? That's 7. We need 1 more. Sock. Now, I want you to find a reason, to abstract a reason for dividing those into 2 groups of 4, on any basis you like. Just think for a moment. All right, gentlemen there?
Words with the letter O in them.
Words
Glove,
with the letter
sock,
O in them.
Nose and rainbow.
Nose, rainbow, glove, and sock. All right, another reason? Gentleman in the middle there?
Words with more than 4 letters in them.
Words with more than 4 letters, all right. Some other reason, something to do with their meaning or anything other than they're just their letters? Let's just think. 2 groups of 4. Gentleman there?
Glove, sock, nose and jumper. Things that you either wear or have on your body.
Okay, fair enough. You wouldn't wear a desk or a rainbow or something of the sort. All right, in fact, you can do this exercise with any 8 words you like whatsoever. The human mind is so good at picking out patterns that the exercise will always work. The last way we use patterns is an analysis, where we analyze something complex down into patterns which we recognize, and then we deal with those patterns. And we're going to do an exercise on that. And what I'm going to do is I'm going to ask Diana to bring someone up.
Would you like to come up? You looked intelligent.
Now, this gentleman is going to hold up this so that you can't see through it, and he's going to describe a shape that he's got up there. And I want you, on your acetate sheets, to draw that shape. Draw that shape on your acetate sheets. Now, okay, everyone ready? Okay, go ahead, speak quite loudly.
There are three separate shapes. On the left-hand edge at the top, there's an oblong, or rectangle, and immediately beneath it, there is another rectangle. To the right of these, there is a shape which looks like a C. The top edge of the C is in line with the top rectangle, and the bottom edge of the C is in line with the lower rectangle.
Okay, thank you. We'll take that, and I'll show you in a moment what it is. Diana, would you like to collect up a few of these? All right, I'll show you what the shape was first. That is what the shape was, and that's how the gentleman was looking at it. Now let's see some of the things we've got here. We've got a C. The gentleman did describe it as part of a C, which says going into shapes we know. There's another one with part of a C there. Again, another one with C. It's an interesting example of using a familiar pattern, but in this case, I wouldn't say misleading, but rather easy to interpret in a different way. Now, the actual shape, where was it? Here. You could actually describe in a rather simpler way. Any suggestions, very quickly, describing that in a simpler way? Any suggestions describing it in a simpler way? The what? An H on its side with its legs dropped down a bit. Yes, I think that's probably the easiest way to do it. So in analysis, we really break things up, but search for familiar patterns at the same time. So we're coming to the end now, and so I'll summarize what I've been talking about. First of all, we were talking about perception, and I was saying perception is probably the most important part of thinking. Most of our thinking takes place in perception. It's only in very specialized situations we have to process things, and in the future we can probably delegate processing to computers, but we as people will still have to do perception. Then that the mind is a wonderful system for turning the world into nice patterns we can recognize. So it's a pattern-making, pattern-using system, and that's wonderful. I want to stress that's wonderful. There's nothing wrong with it at all. It's an absolutely amazing mechanism for doing that. Then, when we're thinking, what we try and do is really we try and rush for the nearest available pattern, because once we can find it, we can stop thinking and we can just follow along the pattern. Now, what's the negative side to it? The negative side is, first of all, we may get the wrong pattern. Or we may get locked into patterns, and once we've been using these patterns again and again and again, it's very difficult for us to shift to other patterns. And very often progress can only come about if, in fact, we do shift to other patterns. And that's why we need mechanisms for shifting out of one pattern into another, and that's where lateral thinking comes in, and we'll be looking at that in another program. Thank you.